Hello there. So we are looking here at synthetic division for a cubic polynomial, but really we can use synthetic division for any kind of polynomial, as long as we're taking this polynomial and dividing it by something in the form of x minus k. So k represents some kind of number, so it could be x minus 2, could be x plus 2, x minus 3. Whatever it is, it has to be in that form where the coefficient here of x is just 1, and then we're adding and subtracting a number there. So if we have that form, then we can go ahead and set up our synthetic division. So you'll notice here, if it's in the form x minus k, then this k, whatever that number is going to go right here on the left-hand side. So if it was x minus 2, then you would have a 2 here. If it was x plus 2, then you would put a minus 2 there. So whatever that number is, if it's a minus, you're going to put basically the opposite. If it's x minus 3, you're going to put a positive 3. If it's x plus 3, you're going to put a minus 3. So always opposite for that one. And that's because the form is already opposite there with that minus. Okay, and then you're going to look here. Notice these are just the coefficients of what our dividend was. So here we have the A, B, C, and D. So those coefficients are going just right here. So initially you set it up and it looks something like this. Oops. We have our, and I tend to use this notation. It's a little different than this one. So then we would do this, A, B, C, D, just like that. So the first thing you always do is you always bring down that first number, whatever that number is. So in this case, it's A. And then what you do is you multiply that times K, or whatever that number is. So we end up getting K times A. And you write that right underneath the next number. From there, you're going to add up the terms, whatever you have there, so B plus KA, and then you end up with B plus KA here, and then you keep doing that same pattern. So this is going to multiply there, and so forth and so forth. So that's the pattern. We call this little number right here, whatever you end up with at the end, the remainder. And we're going to talk more about what that remainder represents, but that would be our remainder. And these here end up being the coefficients of your quotient. And we'll see in this example how that all works out. So we're using synthetic division to divide x to the fourth minus 10x squared minus 2x plus 4 by x plus 3. So that is in our form that we want. I'm going to go ahead and put a minus 3. Remember, we put opposite. And then I'm going to go through and look at all the coefficients. So this has a coefficient of 1. This is x to the fourth, and then it jumps to x squared, which means that we need to put in a placeholder for that x cubed. So I'm putting 1 for x to the fourth, 0 for x cubed, minus 10 for the x squared, minus 2 for x, and then a 4 for the 4. That's my initial setup. I'm going to automatically just bring down the 1, just like that. And so next I'm going to take 1 and multiply it by negative 3, and that gives me negative 3. And then we're going to go down, so 0 minus 3 is minus 3. Now we go multiply. Negative 3 times negative 3 is positive 9. We go down, so negative 10 plus 9 is going to be negative 1. And we just keep on going. Negative 1 times negative 3 gives us a positive 3. going down, minus 2 plus 3 is a positive 1. And then last time, 1 times negative 3 gives us a negative 3. 4 minus 3 is a positive 1. So now that we've finished our pattern here for synthetic division, I'm going to write out our answer. These are all the coefficients of our answer. So if we started out with a 4th degree polynomial, when we're dividing by this 1st degree polynomial, everything is going to go down a degree. So that means we have a 1 here as the coefficient, but it's going to be x to the 3rd. And then we have a minus 3, so it's going to be minus 3x squared minus x plus 1. So that is this, that, and that. And then the last one here, this is our remainder. So remember, anytime we have a remainder, we're going to add that, but divide it by whatever we were dividing by here. So we get x cubed minus 3x squared minus x plus 1 over x plus 3 as our quotient, and that is our synthetic division. Then we move on to the remainder theorem. So the remainder theorem, simply put, is, if we go back over here to our example, whatever your remainder here is, then this tells you, because we are dividing by negative 3 here, then f of negative 3 is equal to 1. All right, let's prove it. So if we have this function x to the 4th minus 10x squared minus 2x plus 4, I'm going to plug in negative 3 all the way through. And negative 3 to the 4th is a positive 81 minus 90 plus 6 plus 4. Plug that all into your calculator, you get 1. So it checks out that whenever you do synthetic division, so when you're dividing with the form x minus k, then whatever that k is can be plugged into your x value here, and the remainder, when you do synthetic division, is going to be your output when you plug that k into that original function. So the remainder theorem, as weird as it sounds, is very helpful actually. So we're going to use the remainder theorem to evaluate the function at x equal to negative 2. So essentially what we're trying to figure out is, what is f of negative 2? Well, in order for us to figure that out, we need to figure out what is the remainder when we do synthetic division here. So I'm taking this minus 2 in the corner here. My coefficients are 3, 8, 5, and negative 7. So 3, 8, 5, negative 7. I start out by bringing down the 3. 3 times negative 2 is negative 6. 8 minus 6 is 2. 2 times negative 2 is negative 4. 5 minus 4 is 1. 1 times negative 2 is negative 2. And negative 7 minus 2 is negative 9. And that is our remainder. So one can assume, because of the remainder theorem, f of negative 2 is equal to negative 9. Now you can go ahead and type that into your calculators and see if that's true, but you'll find out that that is correct. So here we want to show that x minus 2 and x plus 3 are factors of this beautiful polynomial here, nice and long. And then we're going to find the remaining factors. So the way that we know that these are factors is, first, if we can take this whole polynomial here. Or actually, let's first think of numbers, and then we'll work with the polynomial. So think of the number 12. 12 can have the factors 4 and 3. So how do you know that those are factors? Well, if you take 12 and divide it by 4, it gives you 3. So you know that together, those two are factors of 12. So you want to take that same concept and we're going to apply it here with our polynomials. So we know that this is our total polynomial here. And we have x minus 2 and x plus 3 that we want to show that they are factors. Because then if we know that those are factors, then we can figure out the rest of the factors. It's almost as if I were to take this even further. And then we know that 2, 2, and 3 are factors. But let's say, for example, I only told you that 2 and 3 were factors and you need to figure out the other one. Well, you would take that 6, divide 12 by it, and it gives you 2. So we're kind of taking that same concept. But an idea here that we're going to use is that when we take the synthetic division, so let's go ahead and take this polynomial and do synthetic division with this first factor here, x minus 2. So that means we're going to have a 2 in the corner here. 2, 7, negative 4, negative 27, negative 18. Those are the coefficients. Bring down the 2. 2 times 2 is 4. 7 plus 4 is 11. Times 2 is 22. Minus 4 is 18. Times 2 is 36. Negative 27 plus 36 is going to give us 9. And then 9 times 2 is 18. Negative 18 plus 18 is 0. So this is another sort of theorem that we know to be true, is if our remainder turns out to be 0, like it did here, then this checks out as a factor of our polynomial. So what we have left here, which is 2x cubed plus 11x squared plus 18x plus 9, is another factor. And we just divided by x minus 2. So take, for example, here, if I were to want to distribute this all out and FOIL this all out, then my outcome would have to be this original part here. Because all we're doing is taking that polynomial, dividing it by this, and then we're getting our outcome here, which is the other polynomial. So now we have x minus 2 times this polynomial here. Now we're going to continue doing the same thing. X plus 3, we're going to divide this polynomial by it. So I'm going to do that over here. I'm going to have a minus 3 in the corner. My coefficients here are 2, 11, 18, and 9. 2, 11, 18, and 9. Bring down the 2. 2 times negative 3 is negative 6. 11 minus 6 is 5. 5 times negative 3 is negative 15. And 18 minus 15 is 3. 3 times negative 3 is minus 9. Would you look at that? We get a remainder 0. So what does that mean? That means that x minus 3 was a factor of this polynomial. So I can take that polynomial and now it breaks down to x plus 3. And we have these coefficients here left over of 2. We're going down another degree, so x squared plus 5x plus 3. And then don't forget that x minus 2 is still multiplying this all there. So we're kind of slowly breaking down that big polynomial that we started out with, this one here, and we're breaking it down piece by piece with each of those factors. Now the remaining factors we can find right in here. Now that's a nice, easy polynomial here that we can try to factor because it's just a quadratic. So we have 2x and x. And let's say we have 3 and 1, and those are going to be positive and positive. So that is this polynomial here factored out. We're going to multiply it by the two factors there. And now this is our completely factored polynomial. This is the same exact thing as the polynomial that we started out with, 2x to the 4th plus 7x to the 3rd minus 4x squared minus 27x minus 18. But see how we kind of had to slowly work our way there? We first, knowing that this was a factor, divided that big polynomial so we can get a smaller polynomial here that we got here. And then we took that, we broke that down even further, and it gave us this. And then we took that, and then we factored it even further. So that is kind of like the long process of how we take a big, huge polynomial and we break it down into these nice little factors. Very simple and easy to solve factors. If we look here, this is actually the graph of the polynomial that we were just looking at. And so if I were to take that polynomial and set it equal to 0, I now know that I have each of these factors that are being multiplied and equal to 0. Well, I can now set each of those equal to 0. And that's the beauty of being able to factor, because once you factor, then you can go ahead and set up these equations and you can find your zeros from this. So x is going to be minus 3/2, and then x is going to be -1. And if we look closely, there is our -3, that's our 0. There's our -3/2, there's that -1, and then there's that +2. So we found all of those x-intercepts, or all of those zeros, just by factoring there. So we're just going to summarize a little bit of the different ways that we use the remainder theorem, because we used it in a couple of ways now. The first way that we use the remainder theorem is by actually evaluating into a function. So the remainder, whatever that remainder is, gives you the value of f at whatever that k number is. Secondly, when the remainder is equal to 0, we were able to determine that x minus k is a factor of the function. So for example, here, because we determined that our remainder was 0, then we are able to create this first line here that says x minus 2 times the rest of that coefficient is a factor, or are factors of our original polynomial. And then lastly, we're able to see that if the remainder is equal to 0 for that k value, then it turns out to be an x-intercept. So notice here, when we were doing all of these solving here, 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 well, it's actually these values here that we used for synthetic division. See how we got that 2, and then we have that -3. And if we were to have done synthetic division for these two here, then we would also get the same remainder of 0. So being able to use synthetic division is very helpful because the remainder tells us a lot about a function. It tells us its factor, it tells us how to evaluate it, and then it also tells us the intercept of it. Another important test that we want to make sure that we know so that we can take any kind of polynomial and start to analyze it is the leading coefficient test. So the leading coefficient test tells us what is eventually happening to the left or the right of the function. So is it rising up? Is it rising up on both sides? Or is it maybe falling on one side and rising on the other side? So the simple way, or the simple test, is to check the coefficient, the leading coefficient of any polynomial. So let's take, for example, part A here. The leading coefficient is -1. So we have a negative coefficient here. So I'm looking at these two options. And then I want to look at the degree of the function. So the degree here is an odd number. So we have an odd degree here. So based on the test, when we have a function with a negative coefficient and an odd degree, then this is the behavior that the polynomial is going to have. On the left-hand side, it's going to be rising, and on the right-hand side, it's going to be falling. So when it asks me to describe the right-hand and left-hand behavior, I'm going to say rises on the left-hand side. The left-hand side, and falls on the right-hand side. And that was for part A. So let's try this again for part B. We look at the leading coefficient, and that is just a +1. So we're looking at positive coefficients here. And then we look at the degree, we see that it's an even degree. So then this is the behavior. They're both going to be rising. The left-hand side rises and also the right. Left and right hand side. Okay. We have one more here. X to the 5th minus x. The leading coefficient is positive, but the degree is odd. It's an odd number. So that is our behavior. The left-hand side is going to be falling. So it falls on the left-hand side and rises on the right-hand side. So one trick that I like to use with the leading coefficient test is to just think of the two functions x squared and x cubed. So we know that x squared has a positive coefficient and an even degree, and so notice how we know that it looks like a parabola and both sides are rising. X cubed is that cubic function that looks like that. It has a positive coefficient also, but an odd degree, and then notice how we have the end behavior that looks like that. And then if we take that x squared and we put a negative in front of it, well, that's just going to create x-axis reflection. So then that parabola gets flipped over, and then both sides are going to be falling, which is what's happening here. And then if you put a negative in front of the x cubed that has an odd degree, it's going to take that cubic function and flip it, so then it's going to be rising on the left and then falling on the right. So that's just my little tip here. If you ever forget the leading coefficient test, just kind of check x squared and x cubed, because we know x squared is an even degree and x cubed is an odd degree, and then see what those look like and how those change when we put a negative in front. Remember with the leading coefficient test, in the case of x squared and x cubed, it kind of tells us the whole function because that's kind of what the whole function looks like. But when we're doing problems like in part A, B, and C, this is just telling us what's happening at the very end of the function. So for example, in part A, we know that it's rising on the left-hand side and it's falling on the right-hand side, but we don't quite know yet what is happening in between and what it does to get to that point. So the leading coefficient test is only telling us the end behavior. We've looked at the remainder theorem, which helps us to start to find some of those x-intercepts. So we now have another tool where we can start to determine what is happening in between that end behavior. And we're going to continue learning more and more tools to help us determine what is happening in between this polynomial function or any polynomial function. And so the last theorem that we're looking at in this section is called the intermediate value theorem. And this theorem is going to come up a lot once we get into calculus. So we're going to study it a little bit right now before we get into all those calculus topics. And so what this theorem is saying, if we have a polynomial function, so take for example here, this is a polynomial because it's just one little curve there, it's continuous all the way, and we take these values here, x is a and x is b, and notice that the y values that correspond to those are not the same y values. So we don't have something that looks kind of like this, and that's our a and that's our b, and then f of a is the same thing as f of b. That's not what we want. See how these have matching y values? We can't use the theorem if we have endpoints here with matching y values. It just won't work in that case. So we take an example here where we have a and b, and their y values. That was a little weird. Their y values are different. We have different y values. And so what this theorem says is if f is a polynomial function such that f of a is not equal to f of b, well, we proved that already, we see it there, then in the interval from a to b, so the interval from a to b is just kind of like this section right here, what we see in between a and b for x. Then in the interval, f takes on every value between f of a and f of b. So that means that we're going to have a point for each and every one of these y values. Every y value in between f of a and f of b is going to have a point that corresponds with it. And so there's not going to be any holes, there's not going to be any asymptotes. We're going to have a point that corresponds with each and every one of those y values in between f of a, and f of b. So we can see here, this is our polynomial x cubed plus x squared plus 1. If our endpoints here are -2 and -1, so we can see here that's the point that corresponds with -2. That is the point that corresponds with -1. Then the theorem says, because those y values are different, the theorem says that we are going to have a y value in between each of those two y values. So we have a y value here of 1, so y is 1 here, and we have a y value of -3 here. So the theorem says that we're also going to have a y value of 0, because 0 is right here. We're also going to have a y value of -1, because it is in between those y values here. We're also going to have a y value of -2, and anything else in between. So we could have a y value of 1/2, because 1/2 lands right here, and it's between the two y values of these 2 points, so that y value and that y value. If, let's take, for example, y equal to 5. Do we know that that is going to be on that interval? No, we don't, because 5 is greater than this y value here of 1. So we can't assume that the function is going to somehow just kind of shoot up to 5 and then come back to that point. That's pretty much what this intermediate value theorem is saying, is that if we know the ending y values here, then that means we have to have y values all the way through, but it doesn't necessarily mean we're going to have y values anywhere else on this function. So we don't know what's happening past y equal to 1 and y equal to -3. And this just got kind of messy, so I'm going to clear this up so we can see that the theorem is kind of closing it up in between this section here, and that is the x at -2 and at -1. And so we can only determine that we're going to have y values between 1 and -3 thanks to the intermediate value theorem. And that is our notes for this